Alright, so we have a theorem to prove, and again, hopefully, since this is just one theorem, it's a longer one. I'm hoping we can get it done, as I always do, in one video. We'll see what happens. So if n is greater than or equal to 5, then an is simple. And this is continuing what we talked about last time, and it will use those results. So let K be a normal subgroup of an with K not the trivial subgroup. I claim that K contains a 3-cycle. Because remember, we proved last time that 3 cycles generate an when n is greater than or equal to 5. So we really need that. But once we have that, if it has one 3-cycle, then we also know that an acts transitively on the set of 3 cycles. And so you can conjugate this 3-cycle to get all 3 cycles. And then once you have all 3 cycles, you have the entire thing. Okay, so let's write that out. If this holds, then since all 3 cycles are conjugate in an and generate an, and since K is normal in an, we will have that K is equal to an. Conjugation in an, that's fine because K is normal in an. And that means that if you conjugate an element by K by anything in an, you get another element of K. And so, therefore, the fact that K contains a 3-cycle will mean that K contains all 3 cycles, which means that K contains all elements of an, and thus K equals an. So that will mean that if you take any normal subgroup, which is not the identity subgroup, not the 0 subgroup, then it has to be the whole group, and that's what it means to say that an is simple. So now we're going to choose some sigma that is in K but not in E, or some non-trivial element of K, and we can do that because we're assuming that K is not equal to just the trivial group. But we're going to do more than this. We're going to choose some sigma which maximizes the size of the fixed set of sigma. So this is maximizes x in sigma. Maximizes the size of the number of points in x. Here, x is the indices from 1 to n. So we want to choose sigma which fixes the most number of possible indices. And we can choose such a sigma because, okay, well, I'm more analytically minded. So anytime I see a max, I sort of freak out because a lot of times you don't know that a max exists or if that a maximum is attained. You usually have to use supremum, but here an is a finite group always. So there's only finitely many elements. So you just look at them all and choose the one that fixes the most elements, and that's fine. That's not generally when we're dealing with finite groups and finite stuff in general. Maximizing is not something you really need to worry about that much. Alright, so I claim sigma is a 3-cycle. You know what? Oh, yeah, of course. Of course, we want to make sure that sigma is not the identity because the identity fixes everything, and you can't do any better than that. So anyways, suppose that if sigma is written as a product of disjoint cycles, then sigma contains a cycle of length greater than or equal to 3. So if it happens to just consist of one 3 cycle, which contains 3 indices, A1, A2, A3, then we're done, because that's what we want. So now in this proof, there's going to be a lot of arguments by contradiction. So here we're going to have the first one. So assume for contradiction that sigma is not just A1, A2, A3 for some indices A1 through A3. Then sigma must permute additional indices so by parity, there exists A4 and A5 such that sigma of A4 is not A4 and sigma of A5 is not A5. And when I say by parity, what I mean is that AN consists of even permutations. So if we look at sigma, sigma can be written as a product of an even number of transpositions. And so if you were to take this disjoint cycle decomposition and add on more stuff to it, you couldn't just add I guess the if you were to add on like some other cycle, then certainly that cycle would contain at least 2 elements, and so it would permute those. However, what if you were to just take this cycle and expand it a little? Then you might say, oh, well, what if we can just make this, instead of A1, A2, A3, make it A1, A2, A3, A4? That would not work here, because A1, A2, if you have a 4 cycle is not an even permutation, because you can just write it out. Because the parity is, remember, it's going to be 4 minus 1 is 3, which is odd, and so it's not an even permutation. And so therefore, if you're going to, so we know that if you add things outside of, like if you add additional cycles, that you're going to permute at least 2 additional things. And if you just add things to this cycle, you've got to add at least 2 more indices here in order to preserve parity. And so therefore, we do know that there exists A4, A5 such that this holds. And again, we're using that n is greater than or equal to 5, because otherwise you can't find these elements. Okay, let's see here. So now we're going to let tau be A3, A4, A5. Then tau is a 3 cycle, so its parity is even, and so it's in AN. So by normality, we have, let's define sigma prime, a new permutation, to be tau, sigma, tau inverse, sigma inverse. And conveniently, the break in the board is right at where the break I want to show you to prove that this is in K. It's because the things on the left side of the break, you're conjugating an element in K by an element in AN. And by normality, this is going to be in K, and this is going to be in K, and thus the product is in K. All right, so what's interesting about this sigma prime? If sigma fixes x, where x is some index, then x cannot be it cannot be A3, A4, or A5, because we know that sigma moves all of those. It moves A3 either to A1, or if we're adding A4 and A5 onto this cycle, it'll move A3 to A4. And then, of course, A4 and A5, we know by choice that sigma moves A4 and A5. So therefore, x cannot be one of these three indices. And so then tau fixes x as well. And thus, sigma prime x equals x, because tau sigma, tau inverse, sigma inverse, none of those things move x. So then we know that x, the collection of points which are fixed by sigma, is contained in the collection of points fixed by x, fixed by sigma prime. I'm sorry, I don't know where x came from. Probably because I've written it down on the board. Furthermore, what about sigma? Sigma of A2 is A3, which is not A2, obviously. But then, of course, cliffhanger as I change pages. What's sigma prime of A2? Well, this is just tau sigma, tau inverse, sigma inverse A2. Sigma inverse of A2, instead of taking A2 to 3, we look at what goes to A2, and that's A1. So sigma inverse A2 is A1, so we have, here we have tau sigma tau inverse of, I lost my place, tau inverse of A1. Tau doesn't move A1, so this is just tau sigma of A1. And now sigma moves A1 to A2, so this is tau of A2. And tau doesn't move A2, so this is just A2. Okay, so what does this say? So then we've got something that's, we've got an index which sigma prime fixes, but sigma does not fix. So then the size of the fixed points of sigma prime is strictly greater than the size of the collection of fixed points of sigma. And of course, we chose sigma to maximize that thing which I half erased. And so this contradicts our choice of sigma. Okay, so if sigma contains a cycle of length at least 3, then it must be a 3 cycle. What if that's not the case? So now, assume for contradiction that sigma, well, if it doesn't contain any cycle of length at least 3, then it must contain at least, or then it must consist of disjoint transpositions. Remember, this is writing sigma disjointly. So let's assume for contradiction sigma is a product of disjointly many transpositions. Certainly it must contain at least 2 transpositions, because if it were just 1, then it would not be an even permutation. Okay, so now choose K, which is not A, B, C, or D. So we know that sigma contains at least 2 transpositions. Fix 2 of those and choose an index that's not in those any of those 2 transpositions. And let tau be C, D, K. Now we're pretty much going to do the same thing that we did before. Let sigma prime equals tau sigma tau inverse sigma inverse, which is in K. And this is in K for the same reason that sigma prime was in the lower argument, because tau sigma tau inverse we're conjugating by something in an. Of course, tau is an an because it's a 3 cycle. And so yeah, there's that. So that's in K. So if sigma x equals x and x is not equal to k, we have to specify that, then certainly x is not going to be in C, or it's not going to be equal to C or D either. And so if it's not equal to k or C or D, then tau fixes it. And so tau x equals x. And so sigma prime x is just, you let a whole bunch of things act on x, but all of those things fix x. And so this is just x. Note that we had to remove k here because k is in tau. And we really don't know if k could appear in some transposition in sigma. We don't know. But it turns out it doesn't matter because we're going to get a good enough estimate on this, the size of this set. So thus, x sigma set minus k is contained in x sigma prime. Note that sigma a is not equal to a and sigma b is not equal to b. And that's because we have a, b in a cycle and these are all disjoint, so a and b appear only in here and sigma flips them. But sigma prime a, we go through this whole thing again. So tau sigma tau inverse, sigma inverse of a. Sigma inverse of a will, because it's just AB, this is going to be B. And of course tau doesn't move A or B, so B is going to pass right through tau inverse. Sigma is going to switch it back to A, and then it's going to pass right through tau. And then the same exact thing is going to happen for B. Tau sigma tau inverse B, tau sigma tau inverse A, it's going to flip there. Tau sigma, and now it's just going to pass through. This is tau, it's going to go back to B and B. So, the size of the collection of fixed points for sigma prime is going to be greater than or equal to, well, the size of this minus 1. And that's because sigma, or x to this x sigma set minus k is contained in x sigma prime. And so the size of this is going to be less than or equal. The size of this is going to be less than or equal to the size of this. So the size of this is greater than or equal to the size of this, which is equal to the size of this minus 1 for that k. But now, because a and b are not fixed by sigma, but they are fixed by sigma prime, we can add 2 here. And so now we just do some math. This is sigma x sigma plus 1, and neat fact, 1 is greater than or equal to, or 1 is strictly greater than 0. And so we got that. This contradicts our choice of sigma. And therefore, so sigma, if you choose any non-identity element which maximizes the number of fixed points, if it has a cycle of length at least 3, then it has to be a 3 cycle, and it can't not contain a 3 cycle, and so it must be a 3 cycle. And so then k contains a 3 cycle, and so by normality k contains all 3 cycles, and then it contains all of an. And so if you have a normal subgroup that's not just the identity, then it's the whole thing, and that means that an is simple when n is greater than or equal to 5. And that finishes the proof. One other note at the end here, we have these like CELO theorems saying like, oh, if you have a number that divides the order of a group, do you have a subgroup of that size? And using the fact that AN is simple, you can find out that you can find an easy example that it's not always the case. So you suppose that you take a you let your group be A5 and D is 30. The size of A5 is 60, 30 divides 60. But if you have a subgroup of size 30, then the index is 2, and so it divides the order of, and so it's normal, and it's a non-trivial normal subgroup. It contradicts simplicity. And so there you go.